In this video, we're going to do a mixed review of all the different limit techniques we've covered so far. You should really have a list, and it would be best if you wrote it down because people tend to remember things that they write down more than things that they hear. Okay, maybe you like to rehearse it and say it to yourself a lot, or maybe you like to read it a lot, but still writing it down will help a great deal. Now, let's look at my list. And my list looks something like this. And I have this list in this order because it has the procedures in it that I like best at the beginning. Sometimes because I'm more proficient at doing it, or I just enjoy doing those procedures more than later ones. And so your order may be slightly different. I still think no matter what order you're in, this sneak up on it approach, as I call it, um, would be one that you would do at the end, not one you would do at the beginning. Okay. But always, 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 your very first question you should have when you look at a limit is you should look at it and see if you can sub the number in that they're curious about. As X goes to say 16, is 16 in that function's domain? If it is, then just sub it in, and you don't have to go through the rest of this list. So that should always be your first question. I think the sneak up on it method should always be your last method. Some people put it right before trig. I just put it at the very end. At any rate, however your order is, you should write it down. And then every time you look at a problem, you should go through that list and so that it becomes second nature, so that when the adrenaline hits, it doesn't sort of have you throwing everything you can at the paper and hoping something sticks. So you should try to have a system when you practice and when you study so that the system stays with you in the test. So let's try a problem. And I'm going to write it down, and I'm going to give you a minute to decide what you should do with it. Or I won't give you a minute. Maybe I'll give you a couple of seconds. Okay, so here we go. X squared plus 3x plus 2 over x plus 2. So because your teacher's going to mix all these up on the test, she or he is not going to group all the like ones together. So hopefully you took a second, looked at this, and you had a strategy. I'm going to, and I would imagine that some of y'all went, I'm going to factor that because that looks like that can factor. And it does. And these two cancel out and leave you x plus 1. But the thing is, you didn't really need to do that. This one is in this function's domain. And so you could have just put the 1 in right here and gone, okay, 1 squared plus 3 times 1 plus 2 over 1 plus 2 is 3, 4, 5, 6 over 3. So this turns out to be 2. So if you had factored it and put the 1 in, you would have also gotten 2. But this requires you to do some extra work that took some extra time. And if this had been a time test, it might have cost you getting to like the last problem in the test. Maybe it would have cost you 4 or 5 points later on. So you should always decide what it is that you want to do after you verify that the number they're asking about cannot just be substituted in. And of course, you should make a nice little lovely circular box, okay, to get this in. All right, let's do another one. What's the limit as x goes to negative 3 of x squared minus 9 over x plus 3? This is minus 3. So is minus 3 in this function's domain? No, it is not. If you cannot get this x plus 3 to somehow go away, as it were, by factoring or some sort of other technique like that, then this is a two-sided limit. That would have made this a non-removable discontinuity, and you would have had to go through all your other things to say, well, maybe I would need to do a two-sided analysis, what's going from the left and the right. However, this one does factor, and you need to factor it because minus 3 is not in this thing's domain, and we're hoping, since this x plus 3 is the problem, causing the 0 in the denominator, then I can get it to go away, which it does. So this is the limit as x goes to -3 of x minus 3, which is, last time I checked, -6. Now, I haven't talked about this much, if at all. I'm going to write my little sentence and then show you. But when you substitute this -3 in right here to see if it's in the domain, you would actually get -3 squared minus 9 is 0 over 0, because that's a case that you investigate later on in the course. When I sort of mentioned that the first time it came up, I said if you go in for help for the tutoring center and they start talking about this case of 0 over 0 and start going off into some other technique than what you're expecting, they are using the later technique that comes after you do derivatives, and it's a great technique, but you're not ready for it yet because you're still doing limits. So it is 0 over 0, and we'll go over that a great deal after we go through limits. But right now I just need to know what happens if it's 0 in the denominator. So let's try another kind, because again, they're going to mix all these up. Okay, and you need to decide what to do. This is one of those that looks like, oh wait, if I factor out a 3, that's one of those special cases where I have an absolute value over kind of itself without the absolute values. But y'all, what's the very first question you should ask? Can I just substitute this in, and would that be in this thing's domain? And -2 gives you -2 minus 2, which is -4. I think I'm okay with that. Okay, so this is the absolute value of 3 times -2 minus 6 over -2 minus 2. Okay, so you get 12 over -4. You get -3. You okay? Maybe kind of frustrated that I'm showing you all those ones that look so good, and yet you can't use that technique. Okay, because I'm trying to get you to not lose points on the test. So yes, I'm trying to kind of trick you now so that you're not tricked on the test. But what if it had looked like what you were kind of expecting? And you would run through your list. Okay, can I substitute the 2 in? No, that would give me 0 in the denominator. Actually also gives me 0 in the numerator, but I'm not going to talk about that on a regular basis at this point in the videos. It is important later. I just don't want to talk about it now. All right, so you look at it and go, no, 2's not in this domain. And this is what I would do. And I would go, oh, wait, I can actually factor that numerator just a little bit. And now you have that kind of special case where you have the absolute value of something over itself. And if you remember that special case from the last time we did it, then what you would need to do is go, you cannot cancel these. Okay, these right here do not strictly cancel, because this absolute value, if what's in there is negative, it's going to change it positive. And if what's in there is positive, it leaves it positive. So we need to investigate this, right? So we have to do a two-sided limit. All right. Now, as you come in from the left, okay, so you've got 2, and you're kind of thinking of the numbers to the left of 2, that would be like 2.01. Right of 2 would be 1.99. So I'm going to mentally kind of think of this as 3, and I'm going to say, okay, from the left is, well, it would help. I'm thinking -2. Okay, it would help. Y'all are probably freaking out. Okay, so 1.9. Wait, oh my gosh, what had happened to her? So inside I'm thinking negative 2 and I apologize. Okay, so then you'd have 3 times 1.99 minus 2 over 1.99 minus 2. I would lie to you and say, I did that just to see if you were looking, paying attention, and teachers do that all the time. And once in a while, we actually mean it. We did it to see if you were paying attention. Most of the time, I'm a firm believer that we say that because we weren't paying attention for a second and we got caught doing something kind of silly. And we don't want to admit we did something silly. And so we say, we're just seeing if you're paying attention. But yeah, I, I wasn't paying attention. All right. So what you have is 3, and you've got the absolute value of some tiny negative number. And on the bottom, you have whatever this tiny negative number is, you have the same tiny negative on the bottom, right? So this is 3. This is going to turn positive, right? And this same tiny negative is going to be negative. So you're going to have this positive over negative. So this is a negative 1. So this is negative 3. A number to the right of 2 is 2.01 or something like that. So you'd go 3. Absolute value of 2.01 minus 2 over 2.01 minus 2. So this would be 3 times some tiny positive number over the same tiny positive number. So the absolute value of some tiny positive is still positive, and you have the same absolute, you would have like a 2 over a 2. So this would be also positive. So this is going to be 3 times 1. So this is 3. So then you would say, well, okay, I've looked at both sides. One side's equal to negative 3, the other side's equal to 3. So the limit as x approaches 2 of 3x minus 6 over x minus 2 is equal to, it does not exist because the two sides don't match. If they had asked you for one side, you could quote one side versus another, but this is two-sided. Okay, now let's do another one. So luckily in my classes, we have a lot of fun. We do a lot of laughing and, everybody gets along and so we just sort of, but it's good to laugh. It really is. Makes the time go faster. You have to do it anyway. You can do it as a grumpy person or you can try to laugh about it. Trust me, it goes a little faster if you laugh. Okay, now let's talk about this. And so they're talking about x going to 2 from the right, but let's talk about what that would actually do. Okay, so if you substituted a 2 in here, because we should always try, you'd essentially be talking about this concept, and these 2's would cancel. And you're essentially talking about what's happening with cotangent when x is pi as you come in from the right. Well, let's talk about cotangent. So if you remember from trig, cotangent looks kind of like this. And repeats every pi because that was its period. Okay? So this says come into that section from the right. Here is pi. You're coming in from the right. So as you come in from the right, cotangent is climbing. And this turns out to be positive infinity. Now, for my students, I'm thrilled if they can draw me a figure and if they can circle this part and say, okay, this is infinity, and then kind of draw me a little arrow back over here, because I'm just thrilled to know they remember their trig. And I will accept that. Your teacher may or may not accept that. You need to talk with them about how this goes. I mentioned that in earlier videos when we talked about the trig part. So do be sure that you double check with your teacher if they will take a drawing when you're doing trig. I only accept drawings for the trig part. I will not accept a drawing off of your calculator or whatever for any of the other functions. Yes, you can use your calculator to verify what you're saying sometimes, but if you do that, most all teachers will not give you credit, but I do give credit for a trick. All right, let's do the limit as x approaches 2 from the right. So this is a one-sided limit of x cubed minus 4. What do you do? Well, you see if you can sub it in. And 2 is in this thing's domain. And the fact that it's a one-sided limit, that it's from the right side, does not matter. First, this is a polynomial. It's continuous. So what happens is you come in from the right side of a number, and the left side is going to match. But if what you're looking at is in the domain, this plus or minus is irrelevant. You just sub in this number, and you'd have 2 cubed minus 4. Okay, so 8 minus 4 is 4. So the limit as x goes to 2 from the right is the same thing as the two-sided limit and the left-sided limit. It's 4. Okay, what about the limit as x goes to 0 of 8 tangent 5x over 25x? Okay, can you sub in the 0? Nope. Okay, 25 times 0 is 0. Tangent of 0 is also 0, so this is at 0 over 0, but it's not pertinent to you right now. Okay, it's just not in this thing's domain. All right, so you look at it and you think, well, it doesn't really reduce, okay, because this argument 5x of your angle will not reduce into it just doesn't reduce into that 5x. I don't. So, and blank is definitely wrong. So let's think. Maybe we could do that sine. Remember, we had this lovely kind of a identity, sine theta over theta is equal to 1 as theta went to 0. And this one's going to 0. Maybe I can use that because tangent is sine over cosine. So let's see what we can do. So this is x. I have no idea that this is going to work. We're just going to give it a try. So tangent is sine over cosine. And I have this 25x. Okay? Now, here's the limit as x goes to 0. If this is 5x, I need 5x on the bottom. I don't need 25x. But would you be willing to say that 8 sine 5x over 25x is the same thing as 5 times 5x cosine 5x? I'd be willing to say that. Are you willing to say that? So this is that matching that we need where the angle, the argument, is matched down below. So this is going to go to 1. So this turns out to be 8/5 times 1. And cosine of 0 is 1. So this is literally 1 over 1, which is 1. So this turns out to be 8/5. At the end of this video, if you'll look down in the description section, I've included a link to a test, a practice test, and as opposed to just giving you the answers, which is what I've done before, I've worked out the solutions. But I strongly suggest that you take it as if it's a test. Don't use your notes because you won't have those. Don't use any other resources, and just take the test cold, see how you're doing, and grade yourself, as it were, from the answer key. And then if you think you would have made like 50%, that's what you're going to make on the test. So be sure you practice what you missed. All right. So you look at this and go, oh, wait, this is one of those that's going off to infinity plus or minus. So I can take the polynomial over the polynomial and divide by the biggest powered variable in the denominator. So I'm going to squeeze this x squared in. We're going to divide each one of these by x squared. And then I'm going to clean it up so you can see it. So I have x squared over x squared plus 9 over x squared and 2x cubed over x squared. So when I reduce it, and some of y'all may be miles ahead of me by now and skipping steps, but I'm showing steps for people who are um, trying to hold on to all these various and sundry techniques and stay sane. And maybe they can't skip steps yet. Okay, so this is what we've got right now. Now, when you get a very large number in positive infinity or a very large negative number done this way, this is going to go to 0 because a number divided by a huge number, like a huge negative number, like negative 1 million, that's going to go to 0. And this is going to leave me 2 times negative infinity, technically plus 0 over 1. Now, I've seen some students go, oh, this is 2 times negative infinity. No. Okay. If you're racing off to negative infinity, the answer is negative infinity, not double negative infinity, right? So the limit, because it's a huge number, doubling it still just makes it huge because this is a direction, not a value. If that had been 4, doubling 4 would make it 8. That's important. But you're heading off to negative infinity. Doubling it still just makes you heading off to negative infinity. All right, let's just we haven't done one like this. Now, if you try to sub it in, you get 0 on the bottom of each one. You don't get 0 over 0. You get 0 on the bottom. And we haven't really talked about one like this, but the only techniques we talk about are like factoring. This is supposed to be a t right here. T squared plus t. Factoring, square roots, and so forth. It's not a complex fraction, but maybe, you know what? It might look like something I could factor on the top and the bottom if I could kind of squeeze it together into being one fraction. So this denominator right here factors into t times t plus 1. Teaching y'all bad habits. I let my students do this. I don't know if your teacher will let you kind of work within the problem, the statement. Most probably will. So this denominator is t times t plus 1, and this denominator over here is just a t, so it needs a t plus 1. So I multiplied top and bottom by that. And I would have t plus 1. There was a minus there I just covered up. Minus 1 over t times t plus 1. Okay? Which is t over t times t plus 1. And these t's cancel, which is great because that's what's keeping me from using the 0. So I have the limit as t goes to 0 of 1 over t plus 1. So this turns out to be 1 over 0 plus 1. This is 1. So the limit. Do you remember that on your test, if you drop this part here off before you substitute the number in, you're technically wrong, and your teacher should take points off. Don't gripe at them if they did. They're supposed to do that because you're going into you may be going into Calc 2, you may be going to physics, medicine, or whatever. Details matter, right? So, I was going to try to leave one out, but because this is getting a little long, but we're going to do this anyway. X cubed plus 64 over x plus 4. Okay. Now, again, can you sub it in? No. Does it factor? Yes, it does. Okay. It does not cancel. This 4 does not cancel into this 64, and this x does not cancel into that x cubed because they are not factors. X cubed is not a factor of 64. It's a binomial joined by this plus. If you saw the earlier video, you may remember the story about the little hands. Okay, it actually is the sum of two cubes. I like 64. It's a cube and a square. It's kind of cool. All right. So if you don't remember how to factor these, there's an earlier video on how to do that. So this is x cubed plus 4 cubed. You drop the cubes. Square the term in the front. Square the term in the back. Front times the back goes in the middle. If that was a plus, this is minus. This is always plus. And this is x plus 4. And these cancel. And this x plus 4 was the thing that was causing the discontinuity. So they call this a removable discontinuity because you removed it. If you can't remove it, it's a vertical asymptote. All right, so this turns out to be the limit as x goes to negative 4 of x squared minus 4x plus 16. And this turns out to be 48. All right. My husband teases me all the time because even though I was trained as an engineer, my handwriting is awful. I can't begin to tell you how awful it is. All right. So, and this is actually cleaned up just a bit, my poor students. Well, I guess poor y'all too, because you're having to deal with it. Okay, now, so look at this over. And you can't sub in the 8 because when you put it in right here, you'd have 0. You'd actually have 0 in the top and the bottom, but I'm just interested in what happens if I can't have it in the domain. So this one happens to have square roots in it. So I'm going to multiply it by its conjugate and just kind of hope that this works out. So this would be the limit. Remember, you have to write that down every time, even if you're annoyed. Sometimes it's good for you to be annoyed. Keeps you from going to sleep. Okay, now here you go. So in general, you usually don't want to multiply these out because 8 minus x is what you're trying to get rid of. All right, hopefully. All right, so let's go down here. And these we're going to multiply out. So the square root of 8 times the square root of 8 is 8. The two middle terms fall out because of the difference of two squares, and minus the square root of x times the square root of x is minus x. So sure enough, these cancel, and you're left with the limit as x goes to 8 from the left of the square root of 8 plus the square root of x. Now, even though 8 was not in the original function's domain, this is a reduced version of that and an alternate version if you want to think about it. 8 does work here. Okay, so I don't have to do a left-hand limit like you're going to sneak up on it. You just substitute it in. So you have the square root of 8 plus the square root of 8. So this is 2 square roots of 8. And if you've forgotten how to clean these up, this is 4 times the square root of 2. So you pull that 4 out. Got a lot of 2's in here. So this is 4 square root of 2. That's the limit. Sometimes it takes longer to write down the original problem than pretty much anything else. All right. This, I'm going to go way up here because I copied this in. All right. This is the greatest integer function. Sometimes it's called the floor function. Sometimes it's designated as this is the floor function like this. So this would be f of x equals this, or f of x equals this, where it's kind of like a doubled up, squared off bracket. Okay, so both of those mean the same thing. Sometimes I've actually even seen it called int. All right, I don't know how your teacher did it. I usually use this one, but in the interest of I'm a messy writer, I'm going to use this one today. So the limit as x approaches -3 of 3 minus the greatest integer and 4 times the greatest integer. All right, now here, okay, here's -1, -2, -3. This is -3 right here. So at -3, y is -3. To the right, coming in from this side, your y values are on this level line at -3. But on this side of 3, because remember we're looking at what's going on either side of here, coming into this way, it's -4. So do you see how it's got that break, that big discontinuity at this number right here? So we're going to have to look at it from both sides. Now, sometimes students will say, well, it doesn't exist because I can see right there that it doesn't have the same numbers coming in from both sides. That usually does not get you full credit for the answer. Your teacher at this stage in your math career wants to see your justification for why that is. All right, so you have to work this out. So coming in from the left, okay, so coming in from the left right here, coming up on this negative, x is -3, y is -4. So this would be 3 minus -4 over 4 times -4. So this is -7/16. Okay, the limit as x comes into 3 from the right, okay, coming in from the right, okay, what is y doing? That's right here. Y is -3. So this is 3 minus -3 over 4 times -3. So this is -6 over 12, which is -1/2. Okay? So your teacher is going to want to see these values. And then you can say, since they don't match, since it's not the same, then the limit from both sides does not exist. But if you just throw that on there without any justification, I would bet money that they're going to not give you any credit at all, because that's far more likely than taking your guess, okay? Because technically at that point you're guessing. All right. Let's look at the limit. And if you think you're like really tired of going through these problems right now, this is about the length of an average test. So you need to gear up for this. All right. So this is -2. Can you sub the -2 in? No. Can you reduce it or do anything, square roots? No. No, this is pretty simple. So what we're going to have to do is to sneak up on it. Okay. Now we're going to do the -2. Okay. So the number just to the left is -2.01. And the number just to the right is -1.99. All right. So coming in from the left, since I can't substitute the -2 in, I'm going to sneak up on it and kind of try to decide what's going on if I have 1 over -2.01 plus 2. Okay, so this is 1 over a little tiny negative. Don't put -0.01 in there and come up with a number. Okay, it doesn't get to that number and stop or stay there or come in from the other side. At this point, you're going to say this is sort of one of those directional ones we're going off to infinity because this is where it's discontinuous because it has an asymptote, a vertical asymptote. Okay, so let's go back and see the other videos where we're talking about infinities as you approach x or as it yields infinity. So any number divided by a little tiny negative number that keeps getting littler and littler and littler and littler, then this is going to be negative infinity. And this one is coming in from the right. So you'd have 1 over negative 1.99 plus 2, which is 1 over a tiny positive. So this is positive infinity. So if they asked you the two-sided one, this one also does not exist. Okay. If they had asked you just one-sided, you don't have to do both sides, and then you say, thank you really a lot, okay? Because that way I only have to do one side instead of both sides. We really haven't talked about that other identity where it's the limit as theta goes to 0 of cosine theta minus 1 over theta is 0. In the earlier video over the trig functions, you can go back and look at that one, but don't forget that's there. But now we're going to switch topics entirely and talk about continuity. I first brought that phrase up to you in the very first video when we talked about a graph, and the continuity actually is saying, is a function continuous at this point? And if you have a polynomial, that goes on forever, something like this, it's continuous throughout. But what they're saying is they're going to ask you a specific point and say, is this function continuous right here? Let's say this is x is 3. Okay. Now, if it's a polynomial, you could say polynomials are continuous throughout. And some teachers may accept that because they've said that to you. So, if they have said it to you in class and said, y'all, if you know it's a polynomial, it's continuous throughout, you can tell me it's a polynomial, it's continuous throughout, I will give you full credit. Okay? Some teachers have said to you, if I ask you for continuity, I need the 3 considerations that you have to consider. Some of them kind of compress it down to 2, but there's actually 3 things you have to consider, and there's no particular order. Okay? So the limit as x approaches whatever number that you're talking about has to equal some specific number, okay? And as you come in from the left, and as you come in from the right, that has to be the same number, not any L, has to be the same number. And then the function evaluated at that number has to be the same number. So these 3 things have to be true. They all 3 have to be equal to the same. Sometimes people will combine these and say the limit from both sides needs to be L, but usually it's 3, right? All of these have to be true in order for you to say it's continuous. And just saying, yes, it's continuous, may not cut it for your teacher, okay? So you have to do what your teacher has demonstrated for you in class, all right? So if we had some sort of function that looked like this, kind of a piecewise, that's a 4. And the question is this function continuous at x is equal to -2. And if your teacher asks that, okay, I would do the 3 parts, no matter what they said in class, because you can't go wrong with the 3 parts. All right. So the first thing I'm going to do is to say, all right, let's do the limit as x approaches 2 from the left of x squared minus 4 over x plus 2. Because as I come into 2, this would be a -2. As I come into -2 from the left, okay, this part, this second part right here is at 2. This is everywhere but at -2. So as you're coming in from the left and the right, you use this part because that's the left and the right on either side of -2. And at -2, you use that bottom part. Okay? So you would say, all right, can I substitute the -2 in? No, I cannot, because it would give me 0 in the denominator and 0 on the top. But let's just stick with the denominator. So I'm going to try to factor it. And these cancel. Remember, some of your teachers will. I have a specific teacher who used to work for me, and she'd say, I'll tell my students that if they say cancel, I'm going to throw up on their shoes. And I was like, as long as they deal with that. Okay. So, because that was her big thing. So when I subbed for her in her class, I did not use the word cancel. I didn't want her to throw up on my shoes either. All right. Now can you substitute the -2 in? And yes, you can. This turns out to be -4. Okay. Then we would do the limit. I do try to make y'all laugh because, this gets kind of long, whether you're in class or whether you're watching this video. At least if you watch, you can turn this off. But in class, it's kind of hard. All right. So we go, all right, I'm going to factor again. And again, these cancel. And some students will go, can I just use this part over here? Okay, no. All right. You have to learn that for justification, it normally means you can't cut corners. Okay. So this is the limit as x goes to -2 from the right of x minus 2. And since you can just substitute this in, you get -4. Now I'm looking pretty good here. Okay. Now the next question is, what is f of -2? Now, if you're using this function, f of -2 is undefined. But if you go up to the original function, right? Because originally, this is your function that you're talking about. Okay, they specifically said that if you're looking at x is equal to -2, it's just automatically a -4. So f of -2 is defined by the function as -4, and since all these match, then yes, it's continuous. Now be careful with your answer. Yes, it's continuous, not at x is equal to -2. Okay. And if your teacher says why, okay, is it continuous and then has why with a little question mark or explain why or something like that or justify your answer, this up here is the justification, but you really need to put it in your final answer. And you can say, because, uh, and then you would have to you could either write it out in English or refer up to, you can say the limit, as x approaches -2 from the left is equal to the limit as x approaches -2 from the right. And sometimes I'll let you use a run-on sentence here, which is equal to f of -2. So think about your teacher. They've probably given you some hints as to what's going on. Okay. Um, let's do this one. Is f of x equal to 3x squared continuous at x is equal to 0? All right. So you can't reduce it, you can't sub it in, there's nothing you can do, so you're going to have to sneak up on it anyway, but because of the definition. And so the limit as x approaches 0 from the left is 3 over a tiny negative squared, because you're just to the left of 0, so it might be like negative 0.1 or something, which turns out to be 3 over an even tinier positive. So this turns out to be positive infinity. And the limit as x goes to 0 from the right of 3 over x squared is 3 over some tiny positive squared, which becomes an even tinier positive. So this is positive infinity. Now, even though these are kind of sort of both going off in the same, well, they're not kind of sort of going in the same direction. They are going in the same direction, but they are not approaching the same number. These are not continuous because there's some sort of an asymptote at this, and they're both screaming up like this. And you can tell that it's not continuous. It's not making a nice smooth curve, but you can't, depending on your teacher, okay, just bail out. So if you went, what is f of 0? It's not defined, okay? So the answer is no. Depending on your teacher, it depends on how much of this you have to go through. For my classes, I tell them as soon as one of these three is not going to match with whatever's going on, you can bail out and tell me that. Not all the teachers will do that. Okay? So you have got to pay attention to your teacher in your classroom, because what they model and the expectations that they have are what you have to reach. Because when you get out and get employed, what your boss wants, what your customer wants, what your patient needs, what your research partner needs, you have to reach those expectations. Okay? Now, so attached, like I said, if you look at the description underneath, there is a practice test, if you want to call it that. I wouldn't say it's the most stressful problems ever. Depending on your teacher, they may have more difficult problems. I like to, for my students, do things like, what's the limit as x goes to 0 of sine of x times cosecant of x, right? Just to see what they do. This is the limit as x goes to 0 of 1, right? So this is 1. All right. Now, but they know that. I warn them plenty before they get to the test, and I go, look, y'all, if there's trig there, you might want to see if it reduces or something, which goes back to the, can I factor and reduce it or something. So hopefully, and most likely, your teacher has made some sort of hints, okay, about the things that they think they usually include or that they find humorous. Okay, so hopefully they have told you about those before the test. Go back and look at your notes, talk to the other students, be sure you prepare for this. You cannot just splat down an answer and expect to get full credit. You have got to show your work. It needs to be organized. You need to box it in. You need to, if they ask you what the answer is or why, you have to have a nice sentence or a nice mathematical explanation. So good luck. Best wishes on your limits. The next videos we're going to do is derivatives, which actually are a lot more fun. So good luck.